I'm at the University of Bath in the RepRap lab with Adrian Bowyer, who's the inventor of the RepRap machine. Show me one, Adrian, and then tell me what it does.
Okay, I will. It's on my right here. This is the machine. This is an experimental one, which is why it perhaps looks a little bit scruffy. What it does is it takes a plastic filament, which we can see up on our left there. Here it is, and here it is in fact on a reel. It passes it through here, along this tube, and then down to this device here, where it's heated and melted, and it's then pushed out through a very fine nozzle onto this flat bed, and it's then put down in a layer. This extrude head then moves up a little bit, and the next layer is put down, and because the plastic is molten, it welds to the first layer, and it keeps doing that until it's built up a complete object. This, as I say, is an experimental machine, and it's also, in addition to working with plastic, working with metals as well. And so we can print both plastic and metal at the same time in this particular one. Most RepRap machines just work with plastic. On the left here we can see the sorts of things that it does. This is black plastic, not white, which we've just seen, but the principle is the same. There's a gear wheel made in the machine. That's actually a part of the machine itself, as is that. And I mentioned the metal printing. Here are some experimental metal prints. That's the white plastic, that's a computer chip, and this is the metal printing, which is actually being used to make connections to the chip. So we just recently produced an entire microcontroller using the machine, just a couple of days ago, in fact.
As I understand it, once you've got one of these machines, you can take a design from anywhere in the world, download it on your computer, and then print it out.
Yes, indeed. Those designs are stored on various websites, and lots of people put up designs for free. So you can download any of those and print them out. Takes anything from about 20 minutes to a couple of hours, depending on how big the object is. And then you've got one in your hand. And of course, what you've done is to transfer a physical object effectively from one side of the world to the other. Of course, you've had to have the raw materials present locally, but you've then got a finished item which was designed by somebody else. You can also design your own. There are lots of free design programs that you can download from the web, and those design programs will allow you to design your own objects and share them with other people, should you wish.
So, going back 10 years or so, what was your inspiration to design and develop the machine?
Well, I've been interested in self-replicating machines all my life. I can't remember where that came from, ever since I was a child. But we acquired some commercial 3D printing machines, which were very useful, but also very expensive. And when I started using these, the technology seemed to me to be ideal for making a machine that could copy itself. And so I had the idea of making such a machine, and about a year later we set up a project to start designing one, and we had a research student working on that, and he came up with the first machine, which is actually behind me. If I can turn around, it's the machine over there behind those black reels. That's the very first RepRap machine that was ever made.
We're just going to have a quick look.
Of course.
Hey guys, sorry to interrupt.
It's that one up there. That's a design which we call Darwin, the origin of species, of course, and so that was the first one that was made. It would still work if we were to wire it all up again, but the design has now moved on, and we've got much more compact machines that also work much more reliably, and so, as you'd expect, as the developments have progressed, the quality has improved.
And we're about to start a challenge around the world with a series of workshops in which people will come up with further ideas about RepRap. Are you excited by that?
Yes, indeed. I think that getting more people to design more different varieties of the machine can only improve its prospects, and also improve the ability of the machine to make useful things for people, wherever those people are. Of course, it's a machine that reproduces itself, so it's subject to Darwin's laws of evolution. And one of those laws must be that the more successful a machine is at making things, the more likely it is to be successful at reproducing itself. So the more of these designs that come up, that can make the machine give us more varieties of the machine, more species of the machine, if you will, the greater the chances that some of them will be highly successful.
And we're particularly looking at the potential of this machine in developing countries. Can you give us some examples of how that might work?
Yes, indeed. The machine is not very expensive. It costs £200 or £300 to put one together, and that's obviously affordable to a single individual in the developed world, but a small community in the developing world would also be able to afford such a machine. If they've got, for example, a donated computer that they can plug it into, or indeed just plug it into a phone, they can download designs and start printing them. But of course they can also print the machine itself so that they can have more than one should they wish, and they can then start distributing them locally. And they can use them for printing both useful and frivolous objects. People print Christmas decorations on them, and of course, just because someone is living in the developing world doesn't mean that one doesn't need some frivolity. But going to the serious side, you can use them, for example, for printing water filter elements, printing mosquito net clips, printing containers for vaccines, all sorts of useful things like that.
I understand the RepRap can produce about 50 or 60% of itself. Where do people get the other parts?
The other parts of the machine is deliberately designed so the other parts of the machine are as widely available as possible. So, for example, the vast majority of the parts you can buy in an ordinary hardware shop. They're completely standard components. If we can look at the machine behind me, for example, we can see that these threaded rods that form the structure, those are used by the building trade to hold bits of building together, and they're available all over the world. There are one or two specialist components, for example, the electronics, but again, that's available on the internet, which anyone can order from wherever they are. And the advantage of the project being open source is that that electronics is available in open source form, so it's comparatively cheap. And also, there are multiple sources of it, so one can get them from all over the world, from lots of different people.
And why did you make it an open source project?
Well, if you've got a machine that copies itself and you try to protect the design or copyright it or prevent people from making copies of it, what you're really saying to the world is that you want to spend the rest of your life in court trying to stop people doing the machine the one thing it was designed to do. I've got better things to do with my time. The only alternative was to make it open source. And also, when it's open source, given that it copies itself, that maximizes the chances of it reproducing. So it increases, in biological terms, it increases its Darwinian fitness.